All right, the last thing we need to add for this unit is our application problems. We've been practicing quadratic applications, and this is just adding one extra step to it, an application problem, not on a quadratic, but a higher degree polynomial. So we've got 3 that we're going to look at today, and then you've got some more that you'll see in your review sheet, and then more that'll be on our word problem wrap-up over the next 2 weeks. All right, so let's read through this one. The width of a box is 2 meters less than the length. The height is 1 meter less than the length. The volume is 60. Find the length of the box. So specifically they're asking for length, and everything else is given in terms of length. Remember what we said as we were doing our quadratic problems. So I'm going to go ahead and draw the box. As we were doing our quadratic problems, we said you want one single variable. You don't want to have 3 different variables because you can only solve an equation if it's written in one variable. So what's the formula for volume here? Well, volume of a 3D box figure like this is length and width and height multiplied together. So they're giving things in terms of length. Here's the length. The width is 2 meters less than the length, so length minus 2. And the height is 1 meter less than the length. So now I've got everything in terms of length. And they tell me what the volume actually equals, 60. So let's multiply these things together. Length minus 1, and length minus 2. And set it equal to 60. All right, so the first thing I'm going to do, and you can do several different things here. You could distribute the L first, or you could FOIL these together first. And that's what I'm going to do. I'm going to FOIL and leave this L to the end. So when I FOIL, because I'm trying to simplify, I'm trying to get rid of the parentheses. So I multiply the L's together. L in negative 2, L in negative 1, and negative 1 and positive 2. Or negative 1 and negative 2 to get positive 2. And then I'm going to distribute through with the L while also combining these terms that are the same. So when I do that, I'll have L to the third minus 2 and negative 1 is negative 3. And when I distribute this L, that's going to make it L squared, and then positive 2L. I've got a polynomial here. We said this with quadratics, but it's true with any polynomial. When we want to solve it, set it equal to 0. Any polynomial with more than one variable in our problem, and we see variables in 3 places. All right, so I'm trying to solve this question, and I want to think about how do we solve polynomial equations. Well, we could try to factor. How do you factor unless we do a GCF, something like this? So the best thing to do is to go to our calculator and look for solutions. Remember, solutions in our calculator are where does it cross the x-axis. And this is a cubic, so we could have up to 3 separate places we see that happen. So I'm going to type in my equation, and I'm using x's instead of l's, but it's the same idea. And I'm going to graph it. And that looks like that's probably my solution right there for what my length is. So perhaps it looks like it's about at 1, 2, 3, 4, 5. Let's check the table to be sure. Do I see at positive 5 a 0? Yes. If we didn't, if it's not an exact solution, remember the calculator still can give us an answer if we do second trace and 0 and then the left bound, right bound questions. But I was able to easily, without having to do any synthetic division or anything like that, find that my length is a positive 5. So length is 5. Let's figure out width. Width is length minus 2, or 5 minus 2. And height is length minus 1, or 5 minus 1. So the dimensions here are 5, 4, and 3, and they only ask me for length, which is 5. So the difficulty here in the problem is, can we take what they say in the word problem and put it out into an equation and then simplify it? From here, this is what we've been doing the last couple of days, can we solve and find the solutions? And I only care about positive real solutions here. So if there are other solutions, they're negative or imaginary, and we don't care about those. All right, so let's read through this one. The storage company needs to design a new storage box that has twice the volume of its largest box. So again, we're talking about a box. I'm going to draw that on my page. All right, it needs to increase in volume. It needs to double in volume. The current largest box is a 5 by 4 by 3 box. The new box must be formed by increasing each dimension by the same amount. So let's let X represent what we're going to increase each side by. So let's add that to each side. Now let's find our current volume. They don't give it to us this time, but we can easily find it because we know volume is length and width and height all multiplied together. So length times width times height is going to give me 5 and 4 and 3. So currently 5 times 4 times 3 is 60. We want this to double. We want this to be twice as big. So double volume is 120. So I'm going to set up an equation. 3 plus x, and let's switch these because we're used to seeing it variable first. It doesn't matter the order in which you add. The only time that matters is if it's imaginary numbers, and we saw that in our information yesterday. If we have a problem that has the I term first, we switch them. But if there's no imaginaries, it doesn't matter. So we can make it easier for us to solve. And set this equal to our new volume of 120. So our new measurements are going to be something plus 3, something plus 4, and something plus 5. Now how do we multiply together these three binomials? Remember, we did one of these yesterday. FOIL the first two. Combine like terms. And then multiply that with our last one. And you can do the box method if you like. Alright, so I'm going to multiply by x plus 5, what I found from the first time I multiplied, x cubed, 5x squared, 7x squared, 35x, 12x, and 60. So that when I combine all my like terms, I get x cubed plus 12x squared plus 47x plus 60. And then I'm going to be subtracting 120 because I want to set it equal to 0. Now look at all this work I've done on this word problem. But I want to show you something. We're getting ready to type it into our calculator. When I fully simplify it, here's what I have. Let's type that into our calculator. Look at all the work that we did to simplify that down. I can find my answer, it's right here, but check this out. What if I had not multiplied? What if I had left it in parentheses and then just subtracted the 120? X plus 3, in parentheses, x plus 4, and then x plus 5, and then move the 120 over. Guess what? Exactly the same graph. Exactly the same solution. So while this work is all correct, all of this down here is not necessary. Could have done the same thing here. Could have subtracted the 60 over, plugged this into the calculator, minus 60, and been able to find the 5. So if it's a question you know, I'm going to set it equal to 0, and I'm going to plug it in the calculator. Don't feel like you have to simplify it all the way out. So let's finish out the problem. Looking at the calculator, it looked like it crossed the x-axis at 1. Let's see if that's absolutely correct, and it does. So we have a 0 at 1. So that means each side of my box up here is going to increase by 1. So my new dimensions are going to be a 6 by 5 by 4. So it says find the increase in each dimension. Well, that's just the 1, but let's double check our answer. It's always wise to take a second and plug this in. So is 6 times 4 times 3, I'm sorry, is 6 times 5 times 4 going to give me 120? And it does. So I know that I did this correctly. Now our last problem is super important because this problem, I've seen something like this on every single release test. I've seen evidence of questions like this on old EOCs when we taught this as Algebra 2. So this is a question that they really like to put versions of this on the test. So let's read through this one and see if we can visually think what they're talking about in this problem. An open box is made from cutting a 10 by 15 inch rectangular piece of cardboard by cutting squares from each corner and folding up the sides. So what does that look like? I have a piece of cardboard, a flat piece of cardboard. And I go into this piece of cardboard and I cut out squares from each side. So each square here is x by x. We don't know how big the square is, but because it's a square, each side's the same. And then I cut out an equal size square here, here, and here. And then now I've got 4 different pieces that I fold up. So this side gets folded up, this side gets folded up, this side gets folded up, and this side gets folded up. So this is the bottom of my box. And then I have 4 sides of the box that come up. And they tell me let x represent the sides of the squares. So this piece right here was 10 inches, but I cut off x on this side, and I cut off x on this side. So now this piece from here to here is no longer 10 inches, it's 10 minus 2x. This piece was 15 inches, but I cut off x here and I cut off x here. So now it's 15 minus 2x. Let's come up with an equation that represents volume. All right, so let's write an equation that represents the volume of the box. So we're going to have length of the box, 10 minus 2x, width of the box, and then the height of the box. When we fold up the corners, it's just going to be x. So this is our equation that represents the volume of the box. They don't say anything in the question about what volume equals. So let's look at this. You want the box to have the greatest volume possible. Let's graph this equation and see if we can figure out what that would look like. All right, so this equation does represent something that is cubic. We've got an x here, another x in parentheses here, this is the first power, and an x here that's in parentheses. So what this graph, and because the leading coefficient is positive, this graph ends up doing something like this. And it does have a local maximum somewhere up here in our graph, and this will be on the positive side of B in quadrant 1 when we actually graph it. So you may be wondering, how can we have a maximum volume because this keeps going on forever? Well, we can't have anything down in here because that has negative amounts of x. What about over here? Well, this might be something like, say, a measurement of x being a height of 20. Why would 20 not work? Well, look at this. What's 2 times 20? 20 is 40. 10 minus 40, that gives me a negative value. Well, then why is my volume positive? Because this one, 2 minus 20, 15 minus 40 also gives me a negative value. And so it makes it seem when I multiply these two negatives and get a positive as if my volume is positive. Anything past this point right here where we reach the x-intercept of 0 is not going to be acceptable. So anywhere between where we have our y-intercept down to this x-intercept are the only volumes that work. So currently I can't see what my highest volume is, so I need to change my window. I need to see higher on my y maximum. So let's make it something like 500. I have no idea how high it goes, but it could go much lower than that, but let's see if that works. And there's the maximum of my volume again. All of this over here is not important because it's where my two measurements would be negative, thus making it positive. How do I find that maximum point? Using my calculator. Here's the maximum right here. And we want to go to the left of that, go to the right of that, and guess. And so the maximum volume is 132. It's not an exact answer. A lot of times it will be, but it's not here. 132.04 inches, and volume here is cubed. So then it says, how long should we make the cuts? That's the x value here. That's what our x is. X is how long should the cuts be, and they should each be 1.96 inches. And then it says, what are the new dimensions of the box? We would just plug that 1.96 into the two other equations for the 10 minus 2 times that and 15 minus 2 times that.